Hello, everyone. My name is Bryce Bolin. I'm a postdoctoral fellow at NASA Goddard Space Flight Center. I'm going to talk about the discovery and characterization of Ayló'chaxnim, a kilometer-scale asteroid located inside Venus's orbit. So first, I'd like to talk about what are near-Earth objects. Near-Earth objects are asteroids that come within 0.3 astronomical units. About 30,000 are known as of today. There are five main NEO classes. The first are the Amors, which do not cross the orbit of the Earth, but come within 0.3 astronomical units. Then we have the Apollos, which cross the orbit of the Earth, but have a semi-major axis of more than 1 AU. Then there are the Adens, which have a semi-major axis of less than 1 AU and cross the orbit of the Earth. Then there are the Atiras, which are located entirely within the orbit of the Earth. And then there are the Ayló'chaxnims, which are formerly known as Atiras, which are located entirely within the orbit of Venus. Before 2020, none were known. So why were there no known Ayló'chaxnims before 2020? Well, the reason is that their maximum solar elongation is around 46 degrees due to their maximum aphelion of 0.72 AU. Most surveys only cover sky between 70 and 90 degrees or more from the sun. Therefore, they do not cover parts of the sky where Ayló'chaxnim asteroids are located. How do you find these things? Well, with the Zwicky Transit Facility, we can search for these using its large 47 square degree field of view and the capability of the Palomar 48-inch telescope in which it's mounted on, which can point as low as 20 degrees elevation and reach a limiting magnitude around 20.5 in a 30-second exposure. So using the Zwicky Transit Facility, we observe the region of the twilight sky during 12 to 18 degrees twilight, covering around 40,000 square degrees of sky. This is a sky pointing map showing where the Twilight Survey covered the sky during 2019 September to 2020 January. This is a cumulative distribution showing the sun-centric distance of where the Twilight Survey was able to point. As you can see, about half the fields covered parts of sky where Ayló'chaxnim asteroids could be located within 46 degrees of the sun. So here are the discovery images of the very first known Ayló'chaxnim asteroid, formerly known as 2020 AB2. It was discovered on January 4th in 2020, and 4 30-second R-band images, where it was detected at a magnitude around R18. The asteroid was also recovered in 2020 November and 2021 July. These three epochs of observation from the discovery and the two recovery epochs led to it being numbered 594913 by the Minor Planet Center, and was given the name Ayló'chaxnim by the Palma and Luiseño Indians. Here is the orbit of Ayló'chaxnim. It has a maximum solar distance of 0.654 AU, well within the orbit of Venus, and an absolute magnitude of 16.2. Here is the spectrum of Ayló'chaxnim taken in January of 2020 with LRIS on Keck. It has a reddish slope with a dip at around 1 micron, indicative of S-type taxonomy. This gives it a likely size of around 2 kilometers and an albedo of 0.2. Here is the orbital evolution of Ayló'chaxnim. The aphelion of Ayló'chaxnim in the top panel is plotted in orange, and the orbit extent is plotted in cyan for Venus. As we can see, very recently in history, minus 1 million years ago, Ayló'chaxnim became an inter-Venus asteroid and will remain so for the next 1 million years or so. And the bottom panel shows an example of a long-lived clone or a longer evolution of Ayló'chaxnim. However, the majority of clones impact Venus within 10 to 20 million years, shortening their lifetimes. So we were also able to determine the probability of detecting Ayló'chaxnim with ZTF. The NEO model predicts that there are 0.25 Ayló'chaxnim asteroids that have absolute magnitude brighter than 16.2. Combined with the survey simulation and the completeness estimates of the ZTF survey for finding Ayló'chaxnim asteroid, we determined that we had around 5% chance of detecting Ayló'chaxnim. While these aren't necessarily racehorse beating odds, it may suggest that there could be an overabundance of these objects, that being how we were able to detect it by the small odds of finding it. One additional explanation for this is that there could be an additional source of asteroids located inside the inner solar system, such as in the stability region located within the orbit of Mercury at 0.1 to 0.2 astronomical units. Thank you. So here are my conclusions and QR codes where you can find where this work has been published in MinRAS letters. And there's also a preprint that discusses the survey completeness.